of depletion MOSFETs, enhancement MOSFETs. Then we had seen like what is the should be the operating region of the MOSFET so that it can work as an amplifier. So we had determined that region of operation, it should be saturation. After that, we had seen the concept of transconductance, and then we had taken few cases of depletion MOSFET based amplifiers. So we had covered two cases like the fixed bias and the self bias. So if I can go back, so fixed bias, yes, this was the fixed bias, this we had seen, and this was the self bias configuration that we had seen. Okay, so now we are going to begin our discussion with the self bias configuration only, but this self bias configuration, it will be slightly different than the previous one. How is it different? In the earlier case, the RS, the source resistance RS, it was bypassed using the capacitor CS. But in this case, today, we are going to discuss this self bias configuration where RS is unbypassed, means the capacitor is not connected. In this case, the analysis will be slightly more lengthy and complicated. And for the time being, to make it somewhat easier, we will neglect the effect of RD. We will not consider small RD, the output resistance of the MOSFET amplifier. We will not consider it for the moment to give you an idea. So let's try to make the small signal equivalent for this network. So first of all, what we'll draw? We'll draw the small signal equivalent for this depletion MOSFET. So it is drain and sources. So this is say G S, open circuit between G and S. G, let me write G S. Okay, this is my GM VGS. Okay, small RD I have neglected for the moment to make the analysis somewhat easier. So let's have a look at the other external components like RG. RG is connected between gate and the ground. RG is connected between gate and the ground, and RS is connected between source and ground. Since we do not have any capacitor around RS, so this time this RS will not be eliminated and it will appear in the picture. So I have to draw RS, and RS is connected between source and the ground. Where is the source here? Source is this particular point, the source and ground. Okay, this is RS. Okay, now I can rub this. So this RS source, this point is your source. Okay, now RG is connected between gate and the ground. Where is gate? Gate is this point and ground is this. So this is your RG and RD. RD is connected between drain and the VDD. So as per the rules of AC analysis, it is connected between drain and the ground. Where is the drain? Drain is this particular terminal, drain and ground. So this is your capital RD. Now let us mark the VI V0. So this is your II, the input current, VI, the voltage, input voltage, and this is your I0, and this is the V0. Okay, so now if you notice, this network is slightly more complicated than the networks that we had drawn yesterday. So let's try to determine the three parameters. Those are like Zi, Z0 and AV for this particular case, and we know that this time it will be different. So what will be the Zi? Zi, we know that it is the ratio of Vi and IL. Okay, and if we notice or observe the input side carefully, so we will find that input side is essentially the same. There is no change in the input side. Input side is identical to the networks that we had drawn yesterday. So this time also Zi will be equal to Rg alone. Okay. Now what next is Z0. So what is Z0 by definition? Z0 by definition is it is the ratio of V0 and I0 at 0 volt of Vi. Means we have to short the input voltage and then we have to look into the network from this side and then take the ratio of V0 and I0. So to find out this, what we'll do? So let's see first of all what is Vi. So what is Vi here? So Vi here is this voltage, and this is equivalent to, if I write the KVL here, Vi, it will be equal to VGS plus RS. VGS plus RS. Okay, now what is VGS here? So VGS, let's try to determine the VGS. To determine the VGS, let's apply the KCL, sorry, at the output side. So what will be that? Here it will be I0, and let me also write like this current is, let's say if this is the current ID. ID is the drain current passing through the drain resistor. So ID plus I0, it is equal to GM/VGS. You can see this I0, it is coming from here, ID is coming from here, and this is your GM/VGS. So if you apply KCL here at this node, so you will get this particular equation. And as per the definition of Z0, to find out this ratio, we have to put Vi equal to 0. So if I put this Vi equal to 0, Vi we have determined in the earlier equation that it was the sum of VGS, like this VGS plus VRS. I should write this VRS. It is VGS plus VRS. Okay, that should be equal to 0. So VRS is what? It is the potential drop occurred across RS. So in this case, it becomes VGS becomes equal to minus VRS. Okay, now let's put this VRS back to here. And before we do this, what is VRS? VRS is sum of I naught and ID times RS. I naught plus ID times RS. Because what is the total current coming from here? It is GM/VGS is what? GM/VGS is it is equal to ID plus I naught is your GM/VGS. So this GM/VGS we are replacing with I naught plus ID. So your VRS it becomes minus I naught plus ID times RS. Now let's use this and replace VGS with this. So let me rub some of the parts from here. It is ID plus I naught is equal to GM. Now VGS we have to replace with this. GM is what? It is minus I naught plus ID times RS. Okay, so we have got this equation. Now what we'll do, we'll separate out the ID and I naught terms each side. Like ID terms will be in one side and I naught terms will be one side. Let's see then what do we get. So ID terms if I collect in left hand side, so it will be 1 plus GMRS okay, and minus ID minus I naught, it will be 1 plus GMRS. Okay, so what did we obtain? That ID is equal to minus I naught. ID is equal to minus I naught. Okay, so ID is equal to minus I naught. Now what is V naught in the circuit? If we look, V naught is equal to minus ID RD. Okay, since the ID current is going upwards, so V naught should be equal to minus ID RD. V naught is what, which potential it is? Output or the output voltage appearing across RD. So this will be equal to minus ID RD, and so if we replace minus ID with I naught, so it becomes V naught is equal to I naught RD. If we take the ratio of V naught and I naught, so what does it become? It becomes only RD. So in this way, we have determined that Z naught for this self bias configuration when RS is not bypassed will be equal to RD alone. So now let's try to find out what is AV. Let me rub this. To calculate AV, so we have to use the same equation, like VI is what? VI is the sum of VGS plus VRS. Okay, VI, that is potential across this point and this point, that is equal to this VGS plus VRS. So what is the VGS from here? VGS from here, it becomes VI minus VRS. VI minus VRS. After that, what is ID? ID here, or like if I apply the KCL here. So ID is equal to GM/VGS. Now where is this I naught? If I apply the KCL here, so I naught, you must keep this thing in mind that I naught should be included only for the Z naught calculations, because by the definition Z naught is the ratio of V naught and I naught. So that's why in the in the situations where the Z naught cannot be calculated just by the observation, there you have to include the term I naught in your analysis. Whether the KVL or KCL rules, you have to include the I naught. In rest, any of the analysis, you need not to include I naught. So as we are trying to determine the AV, so we should not include I naught. So in this way, so ID will be equal to GM/VGS itself. And what is VGS? We already know. We have determined in the previous equation that it is VI minus VRS. Okay. And now what is VRS? VRS I can write as minus ID/RD. No, VRS is what? It is ID/RS. It is GM VI. VRS is the ID/RS. Because ultimately which current is coming over here? It is the same ID current which is flowing in this output loop. Okay, so that's why VRS will be equal to minus ID/RS. So can we calculate, can we get the expression of ID from here? Like ID terms can be obtained one side and other terms can be left another side. Like it will be what? It will be GM VI upon 1 plus GMRS. GMVI upon 1 plus GMRS. So this is ID. So what is V naught? V naught is again minus ID/RD. Okay. Now let's use this ID what we have determined here to get the ratio. So let me rub about the equations. So it is V naught is minus GM RD times VI upon 1 plus GM RS. So what will be this ratio? This ratio will be V naught by VI ratio, that is the gain, it will be minus GMRD upon 1 plus GMRs. This will be the gain. So we have seen that the analysis, it becomes slightly complicated when the RS is not bypassed, and we have further reduced the complications here by not including small RD. So if we include small RD also in the picture, then the complexity of the analysis will increase. So this main idea was to give you an impression like how the analysis is done. So since we have scarcity of time, So we will be skipping some of the configurations. So like common gate configuration, the procedure will remain same. Like you have to apply this normal your electrical analysis or electrical analysis rules like KVLs and KCL in the input and the output side to determine the required ratio. For ZI, it will be what? VI and II ratio you have to obtain. For Z0, you have to obtain the ratio of V0 and I0 at 0 volt of VI. And for the voltage gain, you have to get the ratio of V0 and VI. All of these like parameters, they can be simply obtained by using the KVL and KCL rules. The length of the analysis can be more, but it is simply the KCL and KVL and then the rearrangement of the terms in order to get what ratio you want. So this was the gate source follower, and this example we had already done in the previous session itself. Yes, so I will discuss this enhancement MOSFET also, feedback bias. So this we will try to analyze as per the detailed discussion. So we have to find out the same that there is ZI, Z0 and AV for this particular network also. So what we'll do, we have to draw the its small signal equivalent. So let's try to draw. So first of all, we'll draw the small signal equivalent of the MOSFET. So what will be that? G and S open circuit, drain and source, it will be the GM-VGS. Again, I will be excluding small rd in order to keep the analysis easier. So this will be what? This will be GM-VGS. Okay, this is the drain. This is the gate. Okay. Source, it is at ground. So if this is the source, the source lies at the ground potential. We can observe from the network. Source is at ground. Then RF. RF is connected between gate and the ground. If this is the VI is applied at the gate terminal. This is your II. Okay. So RF, the feedback resistance, it is connected between the gate terminal and the drain terminal. This is, I'm writing the gate here. The gate and drain. So this is RF. Okay. Then remaining RD, this capital RD, it is connected between drain and the VDD, or I should say the drain and the ground. This is capital RD. It is connected between drain and the ground. Then this is your V0, potential V0, output voltage, and this is the I0. Okay. So what we have to do here, we have to find out the ZI, Z0 and AV. So to calculate ZI, can we do it in the same way we had done earlier? Like simply take the ratio of VI and II. Will it be simply equal to some resistance? No, because you can notice yourself that this time the network is different. There is a feedback path or the connection path between the input and the output. So that's why VI and II ratio cannot be simply written as some resistance. Okay, so we have to do somewhat detailed analysis. So let's, what we can do, we can apply KCL here. Okay, so what is KCL? Let's apply, this is what current? This is II. II current is passing through RF, and let's apply the KCL at this point. So what will be that? II, that is the input current, it is equal to GM VGS. This is the dependent current source, that is GM VGS plus one current is also going here in RD. That is, we can write that as V naught by capital RD. Okay, we will not include I naught because I have told you that I naught will come in the picture only when we have to determine the Z naught, because we have to calculate the ratio of V naught and I naught. Here we have to get the ratio of VI and II. That's why there should not be any I naught in this expression. So can we calculate V naught from here? V naught will come out to be II minus GM VGS. Now what is VGS here? VGS, this potential is what? This is equal to VI. Okay, so II minus GMVI into RD. Into RD. That becomes your V naught. Because we have to eliminate or we have to express the undesired parameters in the form of desired parameter, because we had to take the ratio of Vi and II. So V naught is coming in the expression, so we have to eliminate V naught and we need to express V naught in terms of the desired quantity, say Vi and II only. Okay, so that's what we have done here, that V naught here it is expressed in terms of II and Vi. Okay, so and also we can also apply the normal Ohm's law here to get the II. Now what is II here? It is, we know that current flows from higher to lower potential. So if this is the Vi potential, what is potential at this point? It is V naught. So Vi minus V naught upon Rf. Right? Because II current is flowing through RF. Okay, and we know the potential across each end of the RF. So this side it is Vi and this side it is V naught. So it is Vi minus V naught by RF. Now V naught we have already obtained here, that is in terms of II and Vi. So let's write this. So Vi minus II minus GM Vi. Once you know like what you have to determine and what you have to eliminate, so the analysis, it can be lengthy but you can easily do it. So upon RF. Okay, so V naught has been eliminated from both of the equations, or like using two equations we have eliminated V naught. So now what is left? The expression which is containing terms of only Vi and II. Okay, so if we take the ratio, like we can have the Vi and II terms, we can write separately and then take the ratios. So I am directly writing the ratio Vi and II. It will be equal to Rf plus Rd upon 1 plus GMRD. Okay, this can be easily obtained using this equation. Okay, take Vi terms one side, II terms one side, and then take the ratio of VII. So this is your input impedance in the case of feedback bias arrangement. Feedback bias amplifier, the Zi will be given by this. Okay. So next parameter that we have to determine, that is your Z0. And Z0, we know the definition that Z0 is V0 by I0 at 0 volt of Vi. So let's apply this definition here in the network. So if we put Vi to 0, it means this point it is at ground, right? This point it is at ground, and Vi or VGS, because Vi is equal to VGS in this network, so Vi is equal to 0, so VGS will also be 0. So this source, it will also be vanished. So what will be left in the network? In the network, it will be RD and RF, which will be parallel, because we can see that this end of RD and this end of RF, those are connected together, and this end of RD, it is at ground, this end of RF, this is also at ground. So RD and RF are in parallel. So Z0, it will become RF parallel RD. Okay, so in this way we have determined Z0, and let's also try to determine the AV. So once you have applied the KVL and KCL, so those same set of equations will be used to determine all the three parameters, provided you apply the first set of equations carefully and correctly. Okay, so to determine AV, so we have to take the ratio of V0 and Vi. So we will begin with our previous equation only, that II was what? Vi minus V0 upon RF. Okay, and what is this? It is also equal to Gm Vi plus V0 by RD. These were the only two equations that we had written earlier. This particular set we had written at the like when we had applied the KCL at this particular node. When we had applied the KCL here, then we had written this equation, that II was equal to this, and when we had used Ohm's law in the feedback path, then we had written this. Since both were written for II, so we can equate them. So now if you observe the RHS and LHS of these two equations, so you will notice that these terms contain only V0 and Vi. So if we arrange V0 terms one side and Vi terms one side, so we can easily get the ratio of V0 and Vi. So I will directly write that ratio, that V0 by Vi, that is your AV, will be equal to 1 by RF minus Gm upon 1 by RD plus 1 by RF. If you notice this denominator, this is the parallel combination of RD and RF. So I can also write this as like this term into RD parallel R. So in this way, we have determined all the three parameters for feedback bias amplifier only. So what are some important things to remember here? That we should be knowing like how to draw the small signal equivalent of a network, and then how should we draw the small signal equivalent for the MOSFET, and then we should apply the KVL and KCL analysis carefully. And in order to get like the desired parameter out of Zi, Z0 and AB, we should write the KVL and KCL in the input and the output side and then eliminate the parameter which is not needed. So if we can remember all these things, we can find out these three parameters for any kind of amplifier. Whatever be the biasing arrangement of that particular amplifier, we would be able to determine the required three parameters. So this is again like I guess this is the case of a voltage divider bias for enhancement MOSFET. So here also the results will be quite similar. So this type of arrangement we had already seen in the last session. So here what will be the Zi? Zi, it will be the R1 parallel R2 and Z0 will be equal to RD parallel RD, and since RS is bypassed here, we can directly write these results, and the EV will be minus GM small RD parallel capital RD. So we'll try to solve this particular example here. So this will help you to get more clarification. So if you notice, this is the same network for which we had determined the biasing point or the operating point yesterday. So this feedback bias. So I will be directly using the results what we had obtained in the previous session. Like I will be writing the operating point. So operating point for this, it was ID was 2.8 milliampere and VGS is 6.4 volt. So this means these values I am writing because we had solved this problem yesterday also. But say if any particular network is given to you, first of all you have to determine its operating point by using the procedure that we had discussed yesterday. So means you have to write the equation of the load line, then you have to write the equation of the device, current equation of the device, then you need to solve these two equations parallelly. The quadratic will be formed. You need to get the root, select the appropriate root, and in this way you can determine the operating point. This we have discussed yesterday. So using the same lines only, I have written the operating point, and actually these are the same values that we had calculated yesterday. So today we have to do the AC analysis. Means we have to determine the Zi, Z0 and AB for this particular. So what will be the Zi here? Zi we have determined. The Zi for this, it will be RF plus RD. Okay, before we do, we need to calculate GM. And we know that the GM will be calculated, or it can be calculated only through the DC analysis, because DC analysis, it will give us the value of ID and VGS, and using ID VGS only we can determine this GM. The GM will be twice of ID upon VGS minus VT. Okay, it is twice of 2.8 upon 6.4 minus VT. VT is how much? We can look here, it is 3 volt. So 3.4. So how much is the GM? Let me calculate. It is twice into 2.8 divided by 3.4. It is 1.64 millisiemens. 1.64 millisiemens. Okay, so we have determined GM. So what is the ZI for this? We have determined it was RF plus RD upon 1 plus GMRD. So what is RF? RF here is 10 mega ohm. And what is RD? RD is 2 kilo ohm. So 2 kilo ohm is negligible with respect to 10 mega ohm. So let's not write this 2 kilo ohm. So 10 mega ohm upon 1 plus GM is 1.64 into 2. So if I calculate this, so this will be 10 divided by 4.29. It will be 2.33 mega ohm. Okay, so 2.33 mega ohm will be its input impedance. Z naught. Z naught we had calculated as RF parallel RD. Okay, it will be 10 mega parallel 2 kilo ohm. So which you will know it will be uh, close to 2 kilo ohm and less than 2 kilo ohm. So this will be Z naught. So and what will be the AV? AV was 1 by RF minus GM into RF parallel RD. So 1 by RF. 1 by RF term is 1 by 10 mega ohm. So that will be quite small. So we can ignore this term 1 by RF term because 1 by RF is very small quantity. So it is roughly equal to like 1.64 is the GM and RF parallel RD is, if I roughly calculate, so it is around 3 minus 3. So gain will be around minus 3. So this is how we can determine all the parameters, and this particular example it shows application of both the AC analysis as well as DC analysis. So using the DC analysis we can find out the transconductance at the operating point, and using that GM in magnitude we can calculate the effective ZI, Z0 and the voltage gain of the amplifier. So let's solve another example, and this example is slightly different. So this is one design example. Like here we have been given the parameters of the amplifier, that is in terms of ZI, Z0 and AV are given to us, and using these parameters we have to determine or we need to design the network. So let's read the statement. The statement says that we need to design one amplifier in voltage divider arrangement. RS is bypassed with ZI as 2 mega ohm, Z0 2 kilo ohm and AV as minus 8. And the maximum DC voltage of 15 volt. Also determine the operating point of the transistor. Okay. So if we look at this, so the problem statement also, it does not tell us about the type of the MOSFET, like whether it is depletion or the enhancement. But if we look at this figure, so we can easily identify that this is a depletion type MOSFET because IDSS and VP is given. So this is the typical transfer characteristics of your depletion MOSFET. So we have to design a voltage divider biasing arrangement amplifier using depletion MOSFET. So let's draw the structure. So this is RD. This is depletion MOSFET. This is RS. This is R1. This is R2. RS is bypass. This information was given to us. And VDD is the maximum DC voltage of the circuit. So that will be 15 volt. Okay. So this is your R1, R2, RD, and RS. So basically we need to determine the value of these 4 resistors using the information provided. So it said gain is 8. Gain, and this is the case of bypass RS. So what will be the gain for this? AV will be equal to minus GM capital RD. Okay. So AV is minus, okay. One more thing, AV is minus GMRD, and Z0 is equal to capital RD. We are ignoring the effect of small rd here because small rd is not provided. So we are writing it excluding small rd. So Z0 will be equal to RD. So we have determined here the value of first component, that is RD, and that will be equal to 2 kilo ohm. And then we have this gain. Gain is minus 8. So that is minus 8.
Sir, आप join कर लीजिए.
Minus 8 is equal to minus GM times.
आपको लिंक भेजा है, उस लिंक पे आप देखिएगा.
Capital RD.
नहीं, Teams का है. वो ओपन ब्राउजर में हो जाएगा.
So what will be the GM? GM will come out to be 4 millisieverts. So we have determined the GM RD. Now it says ZI is 2 mega ohm. ZI is 2 mega ohm. And what is the ZI of the voltage divider network? It is R1 parallel R2. R1 parallel R2. So this is equal to 2 mega ohm. Right? And now if we look at this figure, so we are also given the load line, and two X and the Y intercept of the load line are also mentioned. Like it is 3 volt on the VGS axis and the 5 milliampere on the ID axis. So can we also write down the equation of the load line? So we can easily write that it will be VGS is equal to 3 minus 0.6, that will be 5 by 3 by 5, 3 by 5, yes. Yes, 3 by 5 points, that is 0.6 times ID. Okay, VGS equal to 3 minus 0.6 ID. So you can also do the reverse way. Like you can see, like using this equation, whether we are getting these two intercepts or not. So on X axis it will be 3 volt and on the ID axis it will be 5 volt. So it is getting verified. So this is the equation of the load line. So what is the equation of the load line if we look here in the actual network? So this load line equation, it comes out to be VGS. Now what is VG here? VG is this point. It is R2 upon R1 plus R2 into VDD minus IDRS. So if we compare these two, like this particular equation, if we compare this and this, then what will we get? That R2 upon R1 plus R2 into VDD, that is equal to what? 3. And RS is how much? RS is 0.6. So we have determined the RS also. RS is 0.6K. So RD we have determined, RS we have determined, and we have also got two equations relating R1 and R2. One is this, that R1 parallel R2 is 2 mega ohm, and one is this, like R2 upon R1 plus R2 into VDD is 3 volt. So can we also solve this? One equation says that R1 R2 upon R1 plus R2 is 2 mega, and one says that R2 upon R1 plus R2 is how much? 3 by 15. Okay, so using these two equations, so we can also determine R1 and R2. And then now it says determine the operating point of the transistor. How will you determine the operating point? You know the GM. So what was the equation of GM? GM was GM twice of IDSS by VP. What is IDSS? It is 12 milliampere upon VP, mod of VP, that is 5, and 1 minus VGS by VP. How much is VP? VP is minus 5. Okay, so everything is known here except VGS, so you can also determine the VGS, and once the VGS is known, so you can also determine the I. So in this way, if the parameters are given, so by doing the reverse, by following the reverse way, we can also design the network. So this is all what I had to discuss. So we have discussed like the biasing arrangements, different type of biasing arrangement for depletion and the enhancement MOSFETs. We have also discussed like which region of operation to be selected for the amplification purpose, and the role of transconductance, how the transconductance is defined and how the transconductance can be calculated. And then we have learned about the small signal model for the depletion and the enhancement mode, and then application of those small signal equivalent to determine the parameters for the amplifiers, that is ZI, Z0 and AV. So we have taken like separate cases for many types of biasing configuration, and then we have also learned to design, like if the parameters are given, how can we design the network. So this is all what I had to discuss. I hope students might have understood. So if any doubts are there, I'm open for the doubts. Madam, madam.
So thank you, Dr.